Hello and welcome. This is an attempt to re-narrate the original video of my observation from Traprain law, which disproves the flat Earth hypothesis. That is, this observation on screen at the moment proves that the Earth cannot be flat. Furthermore, it provides evidence that supports the standard globe Earth hypothesis. Of course, being a sort of scientific endeavour, it doesn't prove that the Earth is spherical. It can only disprove a given hypothesis. And on this occasion, it disproves the flat Earth hypothesis. So the observation is made of the bridges that cross the River Forth near Edinburgh, and some hills in the far distance, the Fintry Hills and the Campsie Fells. The shot you're looking at the moment is taken with a small compact camera. You don't need a P1000 or P900 to make this observation. And the observation is impossible if the Earth is flat. And the rest of this video will explain exactly why that is the case. Now I'm having to re-narrate it because I had some sound issues, and this means that I'm playing the video and recording narration over the top. So it may be slightly stilted, but hopefully I'll get the points across. The fact that I'm able to make this observation and the fact that it can be repeated by anyone confirms that the Earth is or cannot be flat. If the observation is impossible and the observation on a flat Earth and the observation is made, then the Earth cannot be flat. It's really a very, very simple sort of basic piece of logic. Now, the observation is made from a hill called Traprain Law in East Lothian, and we'll see the details of exactly where that observation was made from. Looking slightly north of due west towards the bridges. Now you see three bridges in the image here. The fourth bridge, as it's known, the railway bridge, is the cantilevered structure slightly in the foreground. There's a suspension bridge behind that, and then three tall towers of the Queensferry crossing. Now my camera is at 210 meters on Traprain Law near the summit. The bridge tower, the central tall bridge tower indicated by the cursor now, is 210 meters above sea level. And this means that anything that lines up with the top of that tower must be 210 meters tall, and anything below the height of that tower must be less than 210 meters above sea level. Yet the hills that we're looking at, actually the hills in shot at the moment, the tallest is 413 meters, but there are hills to the left and right, as we'll see later, which are over 500 meters tall and line up with the top of the tower. And that is what is impossible if the Earth is flat. If the Earth was flat, we should not be able to see the hills below or level with the height of the camera. So this is impossible if the Earth is flat. I've had some criticism for restating that so often, but it's the most important point. It's the whole reason that the observation was made in the first place. If the Earth was flat, I should see a completely different image here. I should not be able to see the tower above the hills in the background. And so because we have an image that is impossible, if the Earth is flat, the Earth cannot be flat. And there is a challenge to flat earthers to actually try to explain how this observation is made. I've made it on two separate occasions. And anyone can repeat it. The observation also, as I say, matches the globe Earth predictions exactly. and so it adds evidence to support the globe Earth hypothesis, if you like. Of course, it does not of itself prove that the Earth is a globe. It simply proves that the Earth cannot be flat. So here we're looking at a side view of the observation. I am standing on a hill called Traprain Law, represented by the green triangle on the left. The hills in the distance are up to 500 meters tall and represented by the green triangle on the right. In the center, or roughly in the center, at 46.5 kilometers away, we have the tower of the bridge, represented by the grey column there on the diagram. Now, because my camera is at the same height as that grey tower, then when I look at the hills in the distance, the tower must line up with a point 210 meters up the hills in the distance, if the Earth is flat. So that applies if the Earth is flat. Now, obviously, if the Earth is a different shape, if it's not flat, whether it's a pyramidal shape or a dodecahedron or a sphere or a rugby ball shape or whatever, this diagram that we're looking at the moment would not apply. The diagram that we're looking at applies on a flat Earth. So once again, here is the observation, and here is what we ought to be able to see if the Earth was flat. We ought to be looking at a point 200 meters up the hills, and yet we have a over 400 meter tall hill that is below the height of the tower. Now, here is a demonstration of to further confirm what I'm stating about being able to see everything lined up with the bridge tower. We have some soda cans here, 2 soda cans stacked on top of each other, and that's repeated 5 times down this 8.5 meter long hallway. There's a little laser pointer showing that the hall floor is flat. That's been marked by the cursor just now. You'll notice that the top of the silver cans is in line with the camera. The camera is being held at the same height as the top of the silver cans, and the tops of the silver cans are all level with each other. They are all the same height in the image. And this is just a simple demonstration of the effect that I would be expecting on a flat Earth. If I have my camera at the same height as an object in the distance, then all other objects that height must be the same height in the image. So I've drawn a red line across the screen here and lowered it down just so that you can see that indeed all the top of all the cans is level. Now I've moved the camera down so that it's level with the bottom of the 2 cans in each pair. And with the camera in this position, the top of the silver cans gets increasingly lower in the image, and the bottom of the orange cans gets increasingly higher in the image. You can see the laser pointer still there, but the location of the camera at the top of the orange cans and every other orange can going all the way back remains at the same height, at the same elevation in the image, the same position, if you like, or relative position in the image. So this demonstration confirms that what I'm claiming about the observation from Traprain Law is in fact true and borne out by experimentation, if you prefer. So here is our image. Now this is taken at 40 times optical zoom. I have placed another red line here which comes down. The central tower of the bridge is at 210 meters. The 2 towers on the left and the right are slightly shorter at 202 meters, and that's borne out by my observation here. So there's no distortion being caused by the camera that would account for anything. And you can see clearly that there are hills that are below the height of that line and other hills that are level with that. Now I go to a zoomed out shot. This is at 20 times optical zoom, and we now can include some more hills which are marked on the photograph here. Some of these hills are well in excess of 500 meters in elevation. They are between 90 or roughly 90 and just over 100 kilometers from the camera. So it's a fairly long distance observation. You do need a clear day with good visibility to see it. My image is taken near sunset. Here is the red line drawn across the image once again to show the alignment for a 210 meter height as we look out towards infinity, effectively at 210 meters. Now you'll see that Earl's Seat and Dunbrack, both of which are over 500 meters tall, lie pretty much on the red line. Meikle Bin is closer to the camera at 570 meters tall and does protrude slightly above the line, as you perhaps would expect on a flat Earth, but all the other hills are very, very clearly showing below the line or on the line, which you most definitely would not expect on a flat Earth. And even Meikle Bin, the line passes very close to the summit, and if the Earth was flat, that line should be less than halfway up, as we shall see later when we look on a curvature modeling app. Now what I've done here is to place a photograph of the Peak Finder website sketch of the hills in the background that I should be looking at, and I've lined that up so that the hills, the horizon line, if you like, matches exactly with the horizon that I'm looking at, and we can locate the hills, Meikle Bin, Earl's Seat. Dunbrack is represented on Peak Finder by a little dot, so there isn't a line for Dunbrack. I've missed out a couple because they refer to lower hills than the ones that are on the horizon. But I've marked Cairnocke Hill at 413 meters, Stronend at 511. All these hills are, this horizon matches perfectly with my observation. There's a red line drawn across so that you can see that it matches up with what we saw on the observation on its own. And if we fade away the Peak Finder overlay, you can see that the horizon does indeed match exactly with the Peak Finder representation. The Peak Finder is a relatively, it's slightly crude sketch, if you like, but it is pretty accurate, and it matches up really very, very well here with all the hills we see in our observation. Feel free to flick back and forwards there and repeat that. So to orient you, this is the location of the observation. The camera was in East Lothian on the right hand side of the screen here. This is on Google Earth, and the hills we are looking at in the background are on the left there where the red lines end. The lines themselves are drawn through the bridge towers, which are on the River Forth just south of Dunfermline, which is marked there, and we will zoom in a little bit later and look at those. So I'm looking just slightly north of west from Traprain Law, and we have a clear line of sight to the Campsie Fells and the Fintry Hills just north of Glasgow. There are no other real obstacles in the way. There are a few small hills, but nothing that's tall enough to get in the way of our line of sight. This is Traprain Law, a rather interesting looking volcanic plug, and this is the trig point at the summit of Traprain Law, 221 meters above sea level, at the benchmark, which is close to the bottom of the trig point tower there. So the top of the hill is 221 meters, and I took my observation from a little bit down the hill at 210 meters. Here we are looking at Google Earth sort of live, And this is an elevation profile of one of the lines drawn through the towers of the bridge. You can see that from Traprain Law, the land slopes down. There's a small hill that we can see over near Haddington, and then a lot of the distance is along the Forth River itself, which means that the line appears flat on this elevation profile because it's all at 0 elevation. And then the land rises up at the hills at Campsie Fells and Fintry Hills. So I also looked on a topographic map to get some accurate heights for elevations. I had the trig point for Traprain Law, but the topographic map confirms this elevation, as we shall see as we zoom in. And it also provides some contour lines, and I actually overlaid this on Google Earth and found the 210 meter contour line and found a location. So I was pretty certain I was at 210 meters. I took 2 or 3 paces further down the hill and set up my tripod so that the camera height would be indeed at 210 meters. So this is Traprain Law, an old volcanic plug of which there are several in this area. We stand up proud of the low-lying farmland around about. So excuse the pause here, but I'm not sure what I said in the original video. So, okay, I think we're now going to scan across past the bridges there that cross the River Forth, of which there are 3, the rail bridge, the 1960s road suspension bridge, and the brand new, completed last year, Queensferry Crossing Bridge, which is the one that has the tall towers that we are particularly interested in. Here are the Campsie Fells and Fintry Hills, and Meikle Bin is indicated here with an elevation of 570 meters, agreeing with the values obtained from the Peak Finder website. Earl's Seat at 578 meters, again agreeing with the Peak Finder. Dunbrack does not have a figure on this particular topographic map, but you can see the contour lines, and a 520 meter contour line is visible. Sorry, 530 meter contour line is visible, and the peak is at 540. So that corresponds. And finally, in the Fintry Hills, we have Stron End, which is indicated at on the topographic map as 511 meters above sea level. So my elevations are confirmed in multiple ways. The elevation of the tower is given on this particular website. Now, there are some websites that state the towers of the Queensferry Crossing are 206 or 207 meters above sea level. But this website details the construction of the bridge and states clearly that the central tower is 210 meters and the north and south towers are 202 meters. So I suspect that other websites and other places have averaged those heights to give the average height of the bridge, if you like. So we know that our central tower is at 210 meters, and we know that our camera was also located at 210 meters. If the Earth is flat, then a line drawn from the camera through the top of the tower would be parallel to the Earth's surface. And therefore, everything that we see along that line should be 210 meters above sea level, and everything below the line should be less than 210 meters. Now, I've used Walter Bislin's advanced Earth curvature calculator to determine whether what we are seeing is what would be expected on a flat Earth, or what would be expected on a globe Earth. And Walter's calculator allows you to put the two models, globe and flat, side by side, and so you can do a direct comparison on the same screen. I've entered the observer height of 210 meters, and I've entered two target objects. One, the bridge tower, which is 46.5 kilometers away and is 210 meters, and a second target, which is the hills in the distance. And I'm just here adjusting the pan setting so that everything will appear nicely on the screen where we want it to be, so that we can see what we're doing. So I'm entering the mountain here. The first of the mountains, I think, is Stronend at 511 meters above sea level and 96.4 kilometers away. Now, without zooming in, everything appears very small on Walter's site, just as it does in real life. I'm just adding the hill in there because I forgot to put the number in. So if we use the zoom function, we can then zoom in to see what the tower and the mountains will actually look like on globe Earth on the right and flat Earth on the left. And we see that the tower should be only coming halfway up the hill Stronend, and yet in our observation we saw it was level with the top of the hill of Stronend. On the right, in a globe version, we see that the tower should actually be above slightly the top of the hill Stronend. So it appears that superficially at this point that neither model is confirmed by the observation that I have made. However, if you add standard atmospheric refraction, which you can do with Walter's calculator, it has the effect of changing the expected observation slightly, and it makes the hill, which is representing Stronend, the top of that hill, match exactly with the top of the 210 meter tower. It has relatively little effect on a flat Earth, although it did adjust the position of the horizon slightly and the position of the object slightly, but still you'd expect the tower to be less than halfway up the hill Stronend. And now we can repeat the whole process for all the other hills that are in the observation. So I think we are going to Cairnock Hill, which is a lower hill that lies between the central tower and the north tower from our viewpoint on Traprain Law. And when you add, we put the figures in for Cairnock Hill, you see that the tower on a flat Earth should be about just over halfway up, or around about halfway up the hill, but on a globe Earth it should be well above the top of the hill. And that exactly matches what we saw in the observation. Next hill we come to is Dunbrack, which is, I forget the distance, maybe 97.2 kilometers, and the height is 540 meters. Once again, the flat Earth predicts that the top of the tower should be less than halfway up the hill, and on a globe Earth the prediction is that it should be pretty much level with the top of the tower. Well, the top of the hill should be level with the top of the tower, which is exactly as we observed in my photograph, or my still taken from a video. Next is Earl's Seat, further away at 101 kilometers, or just over 101 kilometers, and taller at 578. And on a globe Earth, we expect that to be level with the top of the tower because it's further away. Even though it's taller, it appears level with the top of the tower. On a flat Earth, we'd expect the tower to come less than halfway up the hill of Earl's Seat. So that, once again, flat Earth does not match the real observation. And finally, Meikle Bin. If you remember, this was the one hill where on the observation the top of the hill was above the 210-metre line. It's a little bit closer than Earl's Seat, and yes, when we put in the figures 570 metres elevation, we see that the top of the hill in the model is above the height of the top of the tower. On the flat Earth, once again, we would expect the tower to be less than halfway up the hill and not close to the top. So models and predictions match exactly what we see in our observation. So I'm further emboldened to say that the observation is impossible if the Earth is flat. It is impossible for hills to be below the hills that are 400, 500 meters tall, for their peaks to be below the height of the central bridge tower here, as is shown. Camera height 210 meters, bridge tower height 210 meters. Height of the hills up to and over 500 meters. These are all facts established in the video, and I challenge any flat earther to come up with an explanation for how this observation is possible on a flat Earth. And please, if you live nearby and you're a flat earther, go to Traprain Law, climb to the top. It's not that difficult to climb. It's short, fairly steep, and see if you can reproduce this observation. I'm sure you will, and then put your thinking cap on and try and come up with an explanation for it. This observation is impossible if the Earth is flat. I am absolutely convinced of it. I cannot think of a single explanation based on flat Earth geometry that would work. It does, however, agree, as we've seen on Walter's calculator. It does agree with what the globe Earth predicts. So that's pretty much all I have to say. I'd like to thank everybody for watching. I really look forward to seeing some explanations. I hope that people won't, as this is a re-narration, I already know what some people have said. I hope that people will realize that perspective cannot explain this observation. The fact that the camera is the same height as the tower rules perspective out as an explanation. So please offer your explanations if you have them, and welcome to Globe Earth Land.